Okay, stay in touch with your child. You've seen how to run a separate process using exec and fork, and you know how to redirect the output of a child process into a file. But what if you want to listen to a child process directly? Is that possible? Rather than waiting for a child process to send all of its data into a file and then reading the file afterward, is there something to start a process running and read the data it generates in real time? So going back and relating all of this to inter-process communication. What's happening right now is that let's say we have two processes that actually want to communicate with each other. We'll call it P1 and P2. Okay? And P2 can have been forked from P1 and then exec. It doesn't really matter. It's just that both of them are two different processes right now. Now, in terms of memory address space, each one of these processes actually see their own. So if we really think about it, they're very isolated from each other. And your CPU is actually constantly, or not your CPU, but your operating system is constantly switching in between these processes so fast that it looks like you're running multiple things at once. Now, IPC is basically when two processes actually are able to kind of send data in some way to each other so that they can understand each other and do things together. How we're doing it right now is actually these two processes are writing to a file. Let's just say P1 is writing to a file, and then P2 is basically picking it up and doing stuff. And that's how it's and this is like actually, the disk. This is actually disk. So it could be like our SSD in the modern world. So that's how we're actually two processes communicate with each other now. And that could be pretty inefficient because process one has to like write all the data to the file, then close the file, and then process two has to come and pick that up. And it gets tricky because we don't know when process one could finish writing to the file before process two can actually read to the file or read in the file. So we want a better way to do this. We want process one to be able to communicate with process two in real time. Process two communicate with process one in real time. So reading story links from RSS gossip. As an example, there's an option on the rssgossip.py script that allows you to display the URLs for any stories that it finds. So, okay, fine. The script has some sort of option that allows us to see the output. Okay, now you could run the script and save its output to a file, but that would be slow. It would be much better if the parent and child process could talk to each other while the child process is still running. Since I created you, you never write, you never phone. Whatever. Okay, so connect your processes with pipes. So we can have this real-time communication, hence pipes. So you've already used something that makes live connections between processes, pipes. So remember, we can have two processes kind of connect to each other through this pipe operator. All the output from one process becomes the input of another process in real time. So as we output something with one process, say process A, so given process A here, any sort of output to std out gets fed as input to std in of process B, okay, in real time. So the pipes are used on the command line to connect the output of one process with input of another process. In the example here, you're running the rssgossip.py script manually, and then passing its output through a command called grep. The grep command finds all the lines containing HTTP right here. Piped commands are parents and children. Wow. Whenever you pipe commands together on the command line, you are actually connecting them together as a parent and child process. So in the above example, the grep command is the parent of the RSS gossip.py script. That's very interesting. So if we had a command that did A pipe B, for example, this is actually child pipe parent, because it makes sense because the parent is wanting to listen into the child. So parent listens to child's output. Okay? So here's how it works. The command line creates the parent process. The parent process forks the RSS gossip.py script into a child process. The parent connects the output of the child with the input of the parent using a pipe. The parent process execs the grep command. So I guess our shell bash is actually doing all this in the background whenever we have a command that looks like this. So when we have a command that looks like this, bash or our terminal, whatever, is going to actually do this exact process here underneath the hood. Okay. Case study. Opening stories in a browser. Let's say you want to run the RSS gossip.py script and then open the stories it finds in the web browser. Your program will run in the parent process and RSS gossip.py will run in the child. Okay, so you need to create a pipe that connects the output of RSS gossip.py to the input of your program. So we want to open the stories it finds in the web browser. So the program has to run the program has to run in the parent process, and RSS gossip is the child that will feed its output as input to this process. Okay. All right. So how do you create a pipe? So we're not doing this in the command line anymore. We're doing it in C. We're gonna pipe two processes programmatically. So what is the API? What is the function call that allow us to do the pipe without using command line? Okay. Okay. So this API happens to be pipe, the C API. So we have the pipe function call. This will allow us to programmatically connect two processes together. Okay, so pipe opens two data streams. Because the child is going to send data to the parent, you need a pipe that's connected to the standard output of a child and to the standard input of the parent. You'll create the pipe using the pipe function. Remember how we said that every time you open a data stream to something like a file, it gets added to the descriptor table? Well, that's exactly what the pipe function does. It creates two connected streams and adds them to the table. Whatever is written in one stream can be read from the other. So when we call pipe, we get two descriptors. Two new descriptors, the read end and the write end. Okay? When pipe creates the two lines in the descriptor table, it will store their file descriptors in a two-element array. So we need to declare an array of integers, just two elements, pass that into pipe, and it'll actually create these file descriptors behind the scenes and then store the IDs into the arrays. So the pipe command creates a pipe and tells you two descriptors, FD1 is a descriptor that writes right here, the right end of the pipe, and FD0 is a descriptor that reads from the pipe. Once you've got the descriptors, you'll need to use them in the parent and child processes. So you have to set it up first. We have to create the descriptor entries using the pipe function with an array of integers passed in, minimally 2 elements, because it's only going to fill 2 elements anyway. So in the child process, you need to close FD0. So child process FD0. That would be standard in. Oh no, FD0 is, oh sorry, not this table, but this one, FD03. Says FD0 is right here. Okay, so in the child, we need to close this one, okay, of the pipe and change the process's standard output, okay, to point to the same stream as descriptor of file of FD1. So the right end, okay, so for the child, if you want the child to be sending data, its output as input, you basically need to rewrite its output from standard output to the right end of the pipe. Okay, that means everything that the child sends to standard output will be written to the pipe. So I'm guessing the parent is going to close the right end of the pipe and then rewrite its standard input to be FD0, which is the read end of the pipe. Okay. Yeah. In the parent process, you need to close FD1, which is the right end of the pipe, and then redirect the parent's process standard input to read the data from the same place as FD0. So these two are copied. And we do this through dup2. So this is the source of what you want to copy into the destination. Okay, what you want to overwrite with. Okay, so we dup here and then we close. Sure. So everything that the child writes to pipe will be read through the standard input of the parent process. So now they're sharing these descriptors and you're just basically redirecting now. Okay, so opening a page in a browser. Your program will need to open up a web page using the machine's browser. That's kind of hard to do because different operating systems have different ways of talking to programs like web browsers. Fortunately, the out-of-the-work actors have hacked together some code that will open web pages on most systems. It looks like they were in a rush to go do something else. They put something together pretty simple using system. So this is like using that regular generic system call that we weren't supposed to be using. It's not good. Your favorite exec. Okay. So, open URL given a pointer to a character which represents URL, essentially a string. We'll create a buffer that's 255 characters called launch. And then we're going to print out this content here into launch. So basically this is a command that represents the URL and the command to start this program with the URL as an argument. Okay, so that's for Windows. So we call system launch to execute this command. Okay, so this is essentially like typing into your terminal. That's what system does. Yeah, this is the way to do it with Linux. This is to do it in Mac. Okay, sure. The code runs 3 separate commands to open a URL. That's 1 command each for Mac, Windows, and Linux. 2 of the commands will always fail, but as long as the 3rd command works, that'll be fine. Okay. Yeah, we should just rewrite this to work in exec. It looks like most of the program is already written. All you need to do is complete the code that connects the parent and child processes to a pipe. To save space, the include lines and the error and open URL functions have been removed. Remember, in this program, the child is going to talk to the parent, so make sure the pipe's connected to the right way. Wow, this is going to be challenging. Okay, let's take a screenshot and let's start working on it. Okay, then let's blow this up. Then let's do this, Then, oh, that's to move. Okay. I think that's good enough. Yeah, it's visible-ish. Probably like this. Okay. All right. So we need to create a pipe. All right. So that would be the pipe command. So it was like, oh, what does pipe return? Let's see. Forgot. Man pipe. Because we need to check for errors too, I bet. Return, 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 return. On success, 0 is return. On error, -1 is return. Okay, cool. So we need to check for -1 before we do anything. Okay, so we'll do this. It's because I flip between mouse and pen. Okay, so if, okay, pipe, I think it's FD equals -1, which means there's an error. We want to fprintf to std error could not create pipe or something like that. Couldn't create pipe. And then I guess we just exit. I think it was to call the error functions. Actually, let's do that. Let's call the error function. Oh no. Let's see. Oh no. You know what? Let's just move this down. You know what? Why is it? Let's just move this down. I think we're supposed to be using. Oh, did I just? Okay. You know what? Do it again. Okay. Let's try that again. Okay. So if pipe FD is equals to -1, meaning an error happened, we'll call error couldn't create pipe. Something like this, I bet. Okay, so then we're gonna create this descriptor, 2 descriptor entries, and then we're gonna fork. So we'll check to see if it's a -1, can't fork process. Otherwise, if PID returned from fork is non-truthy, meaning that's falsy, that's a child process. So this is child. So right here is a child. So what is a child supposed to do? It's supposed to close the read end of the pipe. So I think the read end was FD0. And then dump the right end of the pipe to basically the output, which is standard out, which is 1. So I think it's just like this. How do I close? Is it just close? I need a reference back. Is it just close? Close, yeah. So yeah, exactly. See, close the read end of the pipe, and then copy the right end of the pipe to the standard output here, which is 1. Okay, so it's exactly like that. So, oops. We want to close the read end, which is FD0. And then we want to dump to the right end of the pipe to be standard outputs. So that's 1. That's the number 1 right there. I don't want to erase it because I'll mess everything up. Okay. Then we exec. And then, okay, so this if statement here is just for the child. Otherwise, we're going to be the parent. So we want to then copy the, what is it, the read end of the pipe to standard in on the parent, and then we want to close the right end of the pipe. So FD1. Okay. And then this one here, what will you read from? This one will read from the descriptor of FD0, so standard in. I think we could just say standard in, right? F get S standard in. I think it's just SCD in because we redirected it already. Is it called SCD in? Or can we just do FD0? Because they should be overwritten now, standard in, but do we still call it standard in? Yeah, do we still call it standard in? I wonder. Anyway, so this is what we have. We'll create the pipe, we'll check for an error, okay? And then we'll close the read end of the pipe for the child, and then write the right end of the pipe, like copy that to standard out. Otherwise, like if we had a PID, okay, we're at the parent here because remember fork just clones the current process, so they have the same code. So you have to handle the parent and child scenarios. So then we're going to clone the read end of the pipe because the parent wants to listen, and we're going to then put that into standard in, and we're going to close the right end of the pipe, and this is still the parent. We want to listen and get stuff from standard in. But I'm not too sure about this one. So let's see. Because this, I want to say it's either standard in or it's going to be the read end of the pipe, which is FD0. One of those. Okay, let's do it. Ooh. Okay, cool. So check, then pretty much close the right end of the, clone the right end of the pipe to standard out, close the read end of the pipe for the child. Then on the parent, you want to clone the read end of the pipe into standard in, and then close the right end of the pipe, and then, yes, we listen from standard in because it is connected to the pipe. We've overwritten it, so we can refer standard in, assuming that that is going to be the same as the read end of the pipe. Yes. Cool. Good exercise. Anyway. So yeah, that's great. It worked. The news opener program ran the RSS gossip.py in a separate process and told it to display URLs for each story it found. All of the output of the screen redirected through a pipe that was connected to the news opener parent process. That meant the news opener process could search for any URLs and then open them in the browser. Pipes are a great way of connecting processes together. Now that you have the ability to not only run processes and control their environments, you can also have a way to capture their output. Wait, but you also have a way of capturing their output. Yes, that's true. So we're getting it now. That opens a huge amount of functionality to you. Your C code can now use and control any program that you can use from the command line. So yeah, so just with pipe, you're able to now simulate this flow here or this flow here without writing to file, right? We basically programmatically did this. We did this programmatically, okay, with the pipe system call. So now two processes can talk to each other. Okay, so now that you know how to control RSS gossip.py, why not control some of these programs? So we can do curl wget, mailmut, convert, whatever. Okay. Is a pipe file? It's up to the operating system how it creates pipes, but pipes created with the pipe function are not normally files. So pipes might be files. It is possible to create pipes based on files, which are normally called named pipes or FIFO files. Why would and just so you know, files aren't really files. Like they files in some operating systems, I think like Linux, they aren't like when you write to a file, it doesn't like write to the disk type of file. Like they're just like data structures that are in memory that have the ability to be written as a file in this case. But I think like when you write to a file and everything like that, it's actually in memory until a certain point, then it gets flushed to disk. Is what I remember. So why would anyone want a pipe that uses a file? Pipes based on files have names. That means they are useful if two processes need to talk to each other and they are not parent and child processes. As long as both processes know the name of the pipe, they can talk to it. Great, so how do I use named pipes? Use the make FIFO system call, MK FIFO. If most pipes are not files, what are they? Usually they are just pieces of memory. Yep, the data is written at one point and read at another. What happens if I try to read from a pipe and there's nothing in there? Your program will wait until something is there. So this is like one way where you have two completely different processes, like pipes, right? Two completely different processes with two different address spaces. For some reason, the ability to share some memory in this way using pipes. So I think they all share like a common place because I think the whole point of pipe is to create that shared memory between those two processes, and then they can have that common place um, to read and write data from without affecting their own memory address, I'm guessing. So how does the parent know when the child's finished? When the child process dies, the pipe is closed and the fgetS command receives an end of file input, which means the fgetS function returns 0 and the loop ends. Can parents speak to children? Absolutely. There is no reason why you can't connect your pipes the other way around so that the parent sends data to the child process. So it looks kind of like this, essentially. So we had something like, remember we had something like A and then B, where child's output is received as input to the parent. Well, if you piped again back to A, the output of B gets sent as input of A. So nothing's stopping us from doing that. We just wouldn't close the right ends at B in this case, and we wouldn't close the read end of A at this in this case. We would have to dump them into the appropriate places too. So, can you have a pipe that works in both directions at once? That way, my parent and child process could have a two-way conversation. No, you can't do that. Pipes always work in one direction, but you can create two pipes, one from the parent to child and one from the child to the parent. Yeah, something like that. Parent and child processes can communicate using pipes. The pipe function creates a pipe and two descriptors. The descriptors are read and are the descriptors are for the read and write ends of the pipe. You can redirect standard input and output to the pipe. The parent and child processes use different ends of the pipe. Okay, cool. Death of a process. Interesting. So you've seen how processes are created, how their environments are configured, and even how processes talk to each other. But what about how processes die? For example, if your program is reading data from the keyboard and the user hits Control C, the program stops running. How does that happen? You can tell from the output that the program never got as far as running the second printf. Okay, so the Control C here after asking to enter the name. So it was probably stuck right here. We Control C and we never saw this hello. Okay. Did the operating system just unload the program? Did the fgetS function call exit function? What happened? Well, the operating system controls your program with signals. The magic all happens in the operating system. When you call the fgetS function, the operating system reads the data from the keyboard, and when it sees the user hit Control C, it sends an interrupt signal to the program. Okay. A signal is just a short message, a single integer value. When the signal arrives, the process has to stop whatever it's doing and go deal with the signal. The process looks at the table of signal mappings that link each signal with the function called the signal handler. The default signal handler for the interrupt signal just calls the exit function. So why doesn't the operating system just kill the program? Because the signal table lets you run your own code when your process receives a signal. So yeah, that's a very useful like fact because when you hit Control C, it kills your process, right? The problem with that is that if you're holding on to resources like open files or network connections or database connections and so on, just by killing that, you're improperly disposing of those resources that are very sensitive. And so like you could corrupt data, for example, if you don't properly like clean up. And so you can actually add like an event handler, like a signal handler, that when we do Control C to kill a program, it'll send some sort of signal, an interrupt signal, and your program can read that in and goes, oh wait, I'm about to quit, or I'm about to be forced to quit. So I'm going to run this function here and do everything I need to do to clean up, and then I'll just go kaput, pretty much. So and we do that through like function pointers because we provide that handler. The handler is in the form of a function, and of course, maybe that function is going to be passed as a function pointer to that signal thing, that whatever function we're going to be using. So catching signals and running your own code. Sometimes you'll want to run your own code if someone interrupts your program. For example, if your process has files or network connections open, it might want to close things down and tidy up before exiting. But how do you tell the computer to run your code when it sends you a signal? You can do it with SIG actions. So SIG action is a function wrapper. A SIG action is a struct that contains a pointer to a function. Yeah, you see that? SIG actions are used to tell the operating system which functions it should call when the signal is sent to the process. So if you have a function called die that you want the operating system to call if someone sends an interrupt signal to your process, you'll need to wrap the die function as a SIG action. So SIG action is like that common data structure that we pass around. The SIG action struct contains that function pointer of referencing the custom function you want to run whenever that signal occurs. So that's how it knows. You pass the SIG action structure around, and then within that structure has that specific function pointer for your OS to kind of call to do the custom thing. So this is how it looks like. This SA handler is that function pointer. You just assign the name of the function. Since die is the function we want to invoke, die will be passed in as that function pointer. Okay. So the function wrapped by a SIG action is called a handler because it will be used to deal with or handle a signal that's sent to it. If you want to create a handler, it will need to be written in a certain way. Yeah, so the handler has a specific format because it is a function pointer. So it's a function pointer in the SIG action struct, so then we have to follow the rules of what SIG action SA handler expects as a function pointer. So in this case, it can be a void with one argument called SIG. So yeah, because the handler is passed the number of the signal, you can reuse the same handler for several signals, or you can have a separate handler for each signal. So you could be like a switch statement here to see, if SIG equals SIG interrupt, or if SIG equals SIG kill, else if SIG equals SIG alert, things like that. Your custom function can check for the specific value. So it's not like you have to create different SIG handlers for every single signal. You can reuse the same one because by default, you're supposed to have your function taken SIG integer, which is going to be the code. Handlers are intended to be short, fast pieces of code. They should do just enough to deal with the signal that's been received. So SIG actions are registered with a SIG action function call. So once you've created a SIG action, you'll need to tell the operating system about it. You do that with a SIG action function. So SIG action, given some sort of signal that you want to register your handler against, so it could be like a SIGINT or a SIGKILL or SIGALERT, whatever. You give it the new action, which is going to be the function point, Sure. No, it'll be the address, so the reference, the pointer to the new SIG action, okay? And then the old SIG action is if you pass a pointer to another SIG action, it will be filled with details about the current handler you're about to replace. If you don't care about the existing signal handler, you set this to null. So I'm guessing most of the time we'll set this to null. And then if we want to, so then SIG action is basically going to register this SIG action struct here. So this is actually a SIG action struct value that is a reference to. And then you register this against a specific signal code. Okay. So the SIG action function will return -1 if it fails, and will also set the erno function. To keep the code short, some of the code you'll see in this book will skip checking for errors, but you should always check for errors in your own code. Okay, so the signal handler or the signal number and then the signal handler. See how it's a function pointer returns void. Okay, so your signal handler should return void, nothing basically, and take in one int parameter, cool, or argument, whatever you would call it. And then, so we create the action, we register the handler to it. So this is like a helper function to actually register a signal handler to a specific signal code. So here's the code for that. Basically, we create an action struct, then we assign the handler to the SA handler property, and then I don't know what this is, but then we'll set all these custom things, and then we'll return our SIG action struct containing all that necessary information. And then we can just use that. Um, so this function will allow you to set a signal handler by calling catch signal with a signal number and a function name. Cool. So rewriting the code to use a signal handler. Okay. I'm gonna stop right here. So actually, yeah, I'll stop right here, and then we'll continue tomorrow. Thanks.